Yeah. All right. Can everyone see my screen okay?
Yeah.
It is.
Yes.
All right, so spheres are great. I mean, a lot of people say, you know, physicists love spheres too much and make jokes about spherical cows, but, you know, they're what nature does, right? I mean, if you get enough gravity, then nature will make anything a sphere. Also, it's relevant to what I do. So if you put a star in a piece of gas and that star makes stuff that makes the gas hot, then it will tend to make a sphere, you know, whether it's winds or radiation or supernovae or whatever, you know, first order, it will be a sphere. And this is nice because we can understand spherical things. You know, it's a 1D problem in spherical coordinates, so we can produce analytic models and figure out how this works. So one of my thesis projects was to put a star in a uniform box and then see what happens. So we used a 3D grid partly because we had a 3D code and we couldn't do 1D spherical coordinates, but also because, you know, things like turbulence are important. So we wanted to study how the gas works. But the first order, it was spherical. So it starts out a little non-spherical because it's a Cartesian grid, but eventually it evolves. So yeah, here it is. So it's initially spherical, and then wait, hang on. No, that's not. Wait, it's not. That's not supposed to do that. Okay, so number one is whatever happened here in 5 times I fudged up the universe. So the first time I gave this talk, it was an Astronomy on tap in a pub. So I talked to the organizers, and I decided to use real swearing, and I put these censorship stickers over it. But unfortunately, because the computer in the pub that I was giving the talk in didn't have the fonts I was using, the censorship stickers were basically in random places and sentences, which did some very interesting things that didn't involve censoring any swearing. Okay, so science is about predicting the future. So, you know, people like Newton, when they were demonstrating stuff, they said, well, if you shoot a cannonball far enough, it'll orbit the Earth, you know, which a lot of people who were interested in waging war, you know, were interested in knowing if they showed a cannon at something, would it actually hit anyone? You know, since prehistoric times, people asked, if I eat something, you know, am I good? Am I not good? And to this day, you know, I have a social Slack where the medical channel is largely people saying, this thing has mold on it, am I okay to eat it? Which the answer is usually no. Cesium water friendly is a great question that a lot of students like the answer to. And were it not unseasonably dry in the Netherlands, which apparently is worrying, then if you were cycling to Science Park, which hopefully you're not going to, the answer is that you would get rained on. And there are a couple of, you know, ways the future can work. So a lot of things that we did in school, this was an outreach talk, so a lot of it was directed at people who you know, school physics was the last thing they did. So if you you know, look at most things in school, then the output is fairly well correlated to the input. So things like if you drive your car half as fast, then you'll get there in twice the time. And some examples in physics, you know, like gravity with 2 particles, so the Earth orbiting the sun. But a lot of actual physical systems are nonlinear. So if you change the inputs very slightly, then very quickly the results become unpredictable. They diverge over a certain time. So things like fluid dynamics, you get turbulence and things which make things hard to predict. Gravity with a lot of particles. So, you know, and the n-body equation is nonlinear. And this is great because if you do astrophysics, then galaxies are basically fluids with a lot of particles in them. So these are very nonlinear, and sort of that's why it's a problem. So, you know, as an example why a weather forecast bad. So one of my mum's carers said, can't you just buy a bigger supercomputer and then just you get a better answer, which is partly true, but at some point the information you have sort of limits what you can know. So you basically get a supercomputer, you draw a big grid over the planet, and then you get some data points and then you run it. But because these equations are nonlinear, then over time these things diverge. So one way around that is simply to run a bunch of models. So you start from your initial point and you say, okay, if I change the initial conditions very slightly, what does this give me? You know, for example, if 20 out of the 100 of your simulations you ran said it'll rain tomorrow, then you can say maybe it has a 20% chance of rain. There's probably more complicated statistics to that, but that's the sort of general principle. And this is sort of a problem also for astrophysics, because if you run one very expensive, nice simulation, it's hard to know if your output is solid, or if it will change if you change the inputs very slightly. So predicting the future is hard because physics is an a-hole. Again, the censorship thing didn't work last time, but that's fine. But sometimes it's hard because you accidentally make an explosion that accelerates forever and destroys the universe. So again, back to this problem in 1D. So we were studying nebulae, and we put in gravity because gravity exists. And we wanted to know what effect gravity had on the expansion of the nebula. It turns out if the gas was dense enough, it made it accelerate, which is wrong. So gravity should pull. It should sort of, push stuff back to where it was. But in this case, it was actually causing it to accelerate. And the energy sort of made sense. We basically calculated that it was absorbing about 3% of the potential energy of the gas around it. And we spent a few weeks trying to figure out if we broke the laws of physics, or if there was some physical reason that maybe it was slightly aspherical. So, something was causing it to expand. And we eventually gave up and did something we could publish, which is actually sort of a slightly worrying thing in the sense that, science is not just, doing a bunch of stuff until you find stuff out. You actually try to create a narrative that you can actually publish and is interesting. And there's a lot of things you do that are just sort of dead ends. And this is a sort of a philosophical question that people have before, and we can have again in the questions if you want, but it's something to be aware of.
Sounds like you rediscovered dark energy.
Yeah, I guess so. Yeah, that could be a very bad paper that maybe a very bad referee would accept. Yeah, so another thing you can do is forget to turn on parts of your code. So one thing I like, and I think I've mentioned before in talks, is that the size of galaxies, which are 100,000 light years across, are controlled by the size of atoms, which are not so many light years across. So the reason for this is that galaxies form in dark matter, which we've never found, but we know it exists, and please trust us. And so over time, over the billions of years of the age of the universe, all of this material streams across filaments into these nodes called halos, and this is where galaxies form. And so things that fall into these things get faster, and fast things keep going unless you stop them somehow. And so fast gas basically turns from this collimated flow of gas all moving in the same direction to this random flow of gas particles moving around randomly. And this doesn't look like a galaxy, it looks like a big hot blob of gas. Ironically, it looks like a galaxy cluster, which I will explain why in a second. So how do we slow this down? So the answer is radiative cooling. So there's a bunch of stuff that can cause particles to convert their kinetic energy into radiation that just escapes into the rest of the universe. So, the classical one is having two particles collide with each other, but you can also have various interactions with scattering and so on. I included this diagram because at the time I was giving it in Germany, and it was the only German word I was going to use, so I put it in. And the time it takes to radiate away all your energy is called the cooling time, which is related to things like density squared. And if this cooling time is longer than the age of the universe, you're not going to make a galaxy. If it's shorter, then you might. And so this is the thesis of this paper and other papers in the 1970s. So it's sort of nice that you can say that this microphysics explains why, for example, you get galaxies, but large galaxy clusters are still sort of not fragmented, or why they don't make super huge galaxies. So back to nebulae. So I did a similar simulation, this time with some turbulence, and we put radiation in the middle and expanded. And it was kind of nice. Now I was fairly excited that this was expanding a lot faster than I expected it. But it was a little bit worrying because it wasn't making any dense structures. The turbulent stuff wasn't really collapsing. And after a couple of weeks, we discovered it's because I forgot to turn on cooling, and my boss wasn't terribly happy. Here's the line of code that I should have turned on. It's sort of easy to do in codes which are fairly huge. I should have been more diligent and figured this out, but it happens sometimes. Sometimes the computer itself wants to screw you over. So explosions or radiation bubbles should be spheres unless something stops it being a sphere. But on one particular machine, when I compiled the code, it made a snake. It basically made this diagonal thing that spread across the grid. I didn't know why, and eventually we changed the compiler options and it did what we expected, so I sort of gave it up. But yeah, this is another thing that sometimes the universe, or sometimes computers themselves, will screw you over. So should we actually trust simulations? I mean, simulations have limits because we can't model every single atom in the universe because we don't have a computer that's bigger than the universe. So we have to make some compromises, and sometimes those are bad. You know, sometimes our models just aren't good enough to describe the thing we're supposed to be describing. Sometimes code's for actual problems. So my particular code, which uses a Cartesian grid, if you do a big galaxy survey and you don't have quite enough resolution to really resolve the inner structure of the galaxy, then the galaxies will align with the grid, which is a little worrying. Certain things about simulations are still good, but the alignment is not great. Sometimes the particles are a problem. So when I started my PhD, I was using this grid code, and other people were using particles to model the gas, and all the grid people found that the particle people had a problem with the way their particles worked. They held onto their entropy too much, and you didn't get proper gas mixing and so on. And eventually this was fixed, but this was a huge and very boring conversation in conferences for most of my PhD. And sometimes your model's just bad. You know, if you put in the wrong numbers or if you put in the wrong assumptions, you get the wrong answer out, even if your model otherwise is pretty good. So why do we actually use simulations if there are all these problems? Well, we can't build a real lab in the galaxy. We can't build a real galaxy in the lab. We can build a real lab in the galaxy. So this is sort of important, you know, in order to understand how these things work, because these things are complicated. But we can't rely on them too much. Another thing is they're expensive, and because they're nonlinear and very complicated, they hide the link between the inputs and the outputs. So a big part of running simulations is actually understanding why your inputs do the things they do when you have outputs. You can't just, you know, like if you look at a single equation, you can say, oh yeah, if I increase, you know, the mass of this, then it increases the gravity by this much. So we still need physical intuition and obviously stargazing to actually get all of this. So, you know, science is a process of actually figuring out how to use the tools you're using and not just cranking the handle and publishing what you see. So number 5 is the time I delete all the stars, which, you know, just if you have an array that deletes the first star in a list, make sure you reset the array so it doesn't delete every star, you know, a star every time step until they're all gone. You know, this sort of thing happens, like you wake up and you find all your stars are missing, and you wonder why it is. Okay, so why did I tell you all of this? So, you know, explosions are funny. This is partly why I went into science. You know, doing simulations, actually seeing things appear on the screen was something that really sort of made it come to life for me. Secondly, I spent too long making that animation, and it's a sunk cost fallacy at this point. But also, I feel like making mistakes and you know, admitting to your mistakes is actually a deeper part of what it means to do science. So, you know, we're always trying to be more productive. The number of papers on arXiv every day is sort of scary, particularly because I have to read, or at least read the abstracts of them all. And the scientific method isn't a perfect abstracted process. It's not like a robot just, you know, mixing chemicals together and turning a handle until it gets science out. We all have more to do every day, and our jobs are often unstable if you're a postdoc or a PhD, or even, you know, if your university is going through some problems. And mistakes are part of the process, and we, you know, we try to be honest. It's not like I'm claiming that dishonesty is a good thing, but these things happen, and it's part of the process, and we have to sort of figure it out. So, for example, there was this article a few years ago where someone found that Exxon basically knew exactly how much they were contributing to climate change, you know, decades ago, and they predicted it fairly accurately. You know, this kind of thing is actually just straight up dishonesty, which, you know, leads to this kind of thing. So I wanted to show you some lines from Appy's midterm self-evaluation, which I thought were interesting. So these lines make up half of the weaknesses and threats to the organization. So there's things like, you know, the fact that if you write a funding proposal, there is over a 90% chance that you wasted your time. You know, there's a lot of bureaucracy and other things taking up your time. You know, small people, small groups doing interesting stuff is sort of ignored in favor of larger, sexier projects that you can sell to people as, the next big thing. And stress and mental health and stuff is something that's becoming increasingly a problem, or at least a problem we're aware of. So this constant pressure is bad for science. I mean, to someone looking from the outside, it seems like if you can get more work out of people, it's great, because if you have this view of people as basically turning a handle and making science, then if you get them to turn the handle faster for longer, then they'll make more science. But this isn't really true, and solutions to this problem won't happen automatically. So this last slide is sort of editorializing, and obviously our illustrious founder had opinions about this, but there are various people sort of actually trying to take control of their academic life. For example, there's a recent example where UCSC has been striking for a living wage because it's impossible to live on Berkeley in a salary, and there's been a lot of conflict about this. So if you're interested, then you can read more. The UK is also going through a lot of issues. I mean, the university system may be even more screwed in the next year, because there was an article this morning that says that over 200,000 fewer students will arrive next year, which is going to be a big problem if you rely on student numbers. There are various protests movements. I mean, it's sort of hard if you're moving around and you're not a native speaker or you don't know the area, but things like showing up to climate protests, even for a lunchtime, is something that I feel is quite important, just to show that you're actually engaged in this. There is a Dutch academic union. I don't know much about it, how the Dutch system works, but it's there. But I think more importantly is that API and the university do have quasi-democratic structures, like we have a PhD and postdoc council that communicates with the institute. The faculty and the central PhD councils do a lot of work. Things like outreach are seen as very important for diversity. There was this diversity meeting a while ago, which said, people going into even the area around the university is actually quite important for connecting with people in fairly underprivileged areas, and things like Aspire are quite important. So what I wanted to really say with this is that science is kind of a human thing. It's humans trying to do the best with what they have. And the scientific process is not just someone turning a handle or pressing a button on a computer and science coming out. It's actually people trying to understand the universe in very human ways, and sometimes making mistakes along the way. And so this is a picture of me with a lot of other people who are mostly, white and cis male people from the global north. But I feel like I've taken enough of your time already, so I feel like that's another talk by someone who knows more about this than me. So thank you. Any questions? Should I stop the slide share so we can see the, I can see the participants list as well.
Yeah, maybe leave it up in case somebody has a question about a specific slide. Yeah, either raise your hand or just pipe up.
Well, first of course, right?
Yeah, like I said, it's sort of strange giving it to a completely silent room, because obviously if you don't mute yourself, then... Remember, you can also use the raise hand thing in the participants list, which maybe if I don't see your camera, then... Maybe...
Well, if I can say something then.
Yeah, sure.
First of all, I was sniggering behind my screen, so
Right,
the humor
good.
definitely came across, especially because I'm also doing a lot of simulation things. One of the things which I was wondering whether you're going to, and I'm not sure whether you got strong opinions on this, is the use of testing modules to ensure that more complex code bases actually remain checked and remain valid. But then oh yeah, I was wondering whether you had opinions on that. And then just as a second point, indeed, I really found it nice that you also pointed out the PhD councils and the work councils, because that stuff, even though it can seem very boring, is crucial to be able to get information from one group of people to the other, and just to even making sure that you pass information on about what's going well and what isn't going well can really help change the allocation of funds or efforts or attention. But yes, testing things, if you could talk about that a little bit.
Yeah, so I mean, I think it's definitely important. So, I mean, if you don't test what the recipes you put in, then it's very easy, for example, for me to make a mistake and then not know, particularly if you just dump everything into a big complex simulation. So one thing that I know, for example, the group in LIDA is very keen on is these modular codes where you can really plug things in and out. So this Amuse framework, for example, is a good example of this. So the code I'm using is fairly monolithic. It was published first in 2002 and is basically a block of Fortran that grew over time. So one of the things I found, for example, was I was doing some of the first simulations with it that combined magnetic fields and radiation. And I found that when you did that, then the magnetic field lines heated up when you put radiation in, because people had decided to store the magnetic fields and the radiation in the same place in memory. Which I think if you test them separately, then they work. But I think testing is always a thing, and you will always find problems with the code. In terms of actually mechanically how you do testing, I don't know so much about that. I should be a better programmer, but if you have opinions, then feel free.
All right, thanks. Yep, I was just curious what your opinion was. Thanks.
Yeah, I was thinking as a follow-up on this whole testing thing, because there's basically an infinite amount of things, but almost one can test. Often in big simulations as well, you have prescriptions for a lot of the processes that happen in the code, but then if you look up papers, and there's like 8 other prescriptions you could use, and that creates sort of a huge combination of different prescriptions you could test for all the different things. That way you can keep on trying to see if something works differently. Or do you feel that there should be like what would be a natural limit to stop your testing, because you could test forever and never publish a paper?
I mean, this is the problem, right? That at some point you're pressured to actually publish. And I mean, I spent a lot of my time, in my early postdoc and PhD basically testing stuff. And there is this conflict, right, where you need to publish stuff. And so, because I've been to various careers lunches and people say, oh yeah, so, in business, you have to submit something that's 80% correct, and you can't be completely correct. But also in research, I mean, you can't be 100% sure that everything works perfectly well. I mean, you can test the individual components, so you can compare them to analytic models and say, okay, in this idealized case, it works. But yeah, I think it's hard, and I think it's an intuition thing, and it's the fact that that sometimes if you publish a paper, then someone will say, oh yeah, your thing is wrong. Like this thing about SPH, so this particle-based gas dynamics, where people said at some point, oh yeah, these people have been doing these simulations, if you run this test case, it doesn't work so well. So yeah, I mean, this is a debate, and this is why science is a process, and why I feel like individual papers are not the end solution to anything. They're just a part of the debate and your contribution to this year or this month's part of that discussion.
But tagging on to that, I mean, so we've now got the new publication rules from the RP in terms of also showing your code and how you got to particular results. And there were also journals which are starting up. They haven't quite got as mainstream, in which they will actually also do a code review. And I think that part is also going to become essential, because why should just the formulas, as were in the paper, be checked by a reviewer and not the actual implementation of that? So yeah.
Okay, we've got a couple more questions. One from Lorenzo, I think he was first, and then Ava.
Yeah, so I think it's related to what you already discussed, but do you think that going towards more open science can help with this?
I think definitely. I mean, it certainly stops sort of slightly dodgy science. So there's people who are not completely outright dishonest, but that something about your code is slightly shaky, and that if you change a parameter, it will break. And I feel like open science is an important part of that. I mean, certainly it helps honesty. I think also, sharing your code is important. There are obviously political decisions about whether or not sharing your code is desirable, because if you're a small group and you have some nice code, then if the bigger group gets your code, they can do all the science with it. But yeah, again, politics is always a problem. I mean, does anyone else have opinions about open science? I don't know so much about it. You know, if anyone has opinions, feel free to join the debate. Should we just have this discussion and then go to Ava's question, or Ava, was this related?
Yeah, actually, I was going to ask the same question.
Okay.
Yeah,
Do you have an opinion?
Yeah, so I have an opinion about this. All the codes that I use for my work are open source. Mm-hmm. And I have to say that makes things very easy for many, many different reasons. Mm-hmm. So one is that anybody can reproduce whatever I do if I give all the input parameters that I used and all the additional lines of code. And anyone can see what you're doing and anyone can report mistakes. And I think that helps science in general. So I think it's a very, very good thing to have codes out there. But as you said, there's always this political issue that, it needs to be, we need to make sure that people get the recognition for their contribution to code. And I think that's one thing that is still missing a lot in our community.
Ralph, you want to add something? Yeah, I mean, I think this is a very interesting topic for discussion. Personally, I'm a great fan of open source code and just putting things on GitHub and making sure they are. Personally, I feel that it would help a great deal if especially the younger generation speaks up about this. Mm-hmm. I recently had a discussion in the Monthly Notices editorial board where, strictly speaking, the editorial code of practice of MN already states that editors can deny publication of a paper if the code is not made public. Mm-hmm. In practice, MN has never yet, I think, stopped publication of a paper for that reason. And there are some editors who feel strongly that they need to keep the codes in their own groups. So now the editors, speaking as scientists, secret, because it would disadvantage their postdocs and PhD students if they had to make the code that they had written public. Now, I try to argue against this by saying you also get credit for code if other people use it. And I think in general that is true. I mean, in Antonia and my group, we have developed this transient pipeline called TRAP, which analyzes a series of radio images and tries to find transients in it. And it's now, factually speaking, the standard in radio transient searches. And the paper gets credit for it. And some of the things you can sometimes consider is publish in a journal like Astronomy and Computing, which does code reviews and which is especially intended to publish code that is applicable to astronomy problems. Right? One of the issues sometimes is if you have developed a new code, the mainstream astronomy journals will sometimes say, well, it's only a code that's a computer science problem, unless you have a novel astronomical application to which you can apply the code and demonstrate that it works. You can't publish a paper about that. But, you know, there are journals that won't do that, so you can always find a place for your code. Personally, I feel science gets better if codes are done in an open science way. And I also, by the way, don't think you give away much of your advantage if you are a group developing code and publishing the code, because it is almost always the case that by the time you have a certain result and you publish that result, then you are already developing the code to the next step while you are publishing one thing. So you're always a step ahead of the rest in your development. So I even don't think it is the case very often that if you publish the code that you use for a paper that is now ready to publish, that you immediately lose all advantage on competing groups.
Right. I mean, so for example, I know someone who wrote a module for the code I use, and they're on a lot of papers because everyone wants to know how the code works and you know, get advice on how best to use the parameters, and then they're naturally on the papers. So, I mean, for individuals, I think this is a good thing. I think there definitely is a pressure where, you know, people want to, you know, get the more competitive funding. And like you say, there are individuals who see this as an issue. But yeah, I mean, like Ava said, code is simply better if it's open source and more people have eyes on it and it's well documented and tested and so on. I certainly know if I'm going to release some code, then I make sure it's a bit cleaner than I would otherwise keep it if it was just for me and I was never going to publish it. So is there a way that you recommend younger people actually speaking up on these issues if editorial boards are talking about this?
Well, I mean, internal pressure does a lot.
Right.
I mean, there is a reason why I created bronze, silver, and gold levels in our research data management. Right? I want to stimulate people. At the moment, I don't have consensus to force people to publish code. I mean, I feel that an institute shouldn't work in such a way that the director simply dictates that you can't work here unless you publish your code. It doesn't work that way, right? In an academic community, you need some amount of consensus. But I certainly want to stimulate it. So what I'm trying to do is to say, well, you know, if you do things that are better, in my opinion, for the scientific community, then the institute will reward it.
Right, okay.
And so I think creating that sort of stimulus, it's one of those things where changing the hearts and minds of people is probably better than ordering them around.
Mm-hmm.
And you see that, and what you see is that the opinions are changing, right? Public codes used to be very rare, except in a few cases like Cloudy, where people were very specifically trying to get mileage out of being the owners of a large code base and helping other people to use it. But you're seeing that that's slowly switching around. And in some sense, I think the current generation may be just wiser than older generations, in the sense that people realize that astronomy as a whole has gotten ahead a lot by a lot of code being public domain. I mean, if I look at, for example, the papers that Mark has published in recent times, he explicitly acknowledges a few basis of open source code, especially large Python modules and things like that. First of all, I think it's a very good idea explicitly to acknowledge them. I mean, that is a coin that never dropped with me, but he realized that that should be done. And he also makes his code public for the same reason. Right?
So there are several codes. For instance, AstroPy actually requests you to acknowledge them, and ADS as well.
Yeah.
And that's partly related to their funding, right? At least the ADS.
Yeah, and it's also a case of where the attitude of the community has to slowly change. Also, not only by wanting to acknowledge code, but also by realizing that if you want to stimulate public domain coding, then you have to reward it, right? So in exactly the same way as observatories already for a long time have asked that you acknowledge the use of the observatory when you publish a paper with their data. I mean, that's exactly symmetric. If you've built a telescope, you want people to acknowledge in their papers that they used your telescope because it helps you keep that telescope funded. In the same way, you know, if you built a code, you would hope that people will acknowledge the use of that code because it gives you some credit and it makes people who are looking at your job application actually appreciate why you are a person who is a useful member of the astronomical community. But it's an old problem. And in fact, the problem that we now have with maybe not enough credit going to people who build useful code, we've already had for a long time, and in fact still have, even though less, with people who build telescopes. If you build a good instrument for a telescope, you tend to get less credit for it than if you do research with that instrument and publish papers with it.
Is there a question from someone who hasn't spoken yet, by the way, or a comment or something that people are sort of holding back?
If not, we could wrap up. I think we have a talk next week, right, Common?
Yeah, that's right. So next week is Eva, I believe. So